Hey, 8. Ain't that great? Ain't that great to do chapter 8? Well, guess what? We're doing it. Starting chapter 8. This is section 8.1 on introduction to CIs. That's going to be called confidence intervals, as you see above there. All right, so we're going to start off with a little bit of review, and that'll get us into what we're doing today. A lot of vocab today, a lot of new terms that you need to know. All right, so review statistics versus parameter. Quick recall. Remember, statistic starts with an S, parameter starts with P. And that's how you can tell if it goes with a sample or a population. All right? So a statistic is something that estimates a parameter. Or we take a sample from the population that's used to estimate from the population. So our samples, which are here, all estimate our population parameters, which are there. And commonly we're using proportions, so p hat estimates p. Means, which x bar estimates mu, and standard deviation, s estimates sigma. Now, we're going to use those things in different types of statistics. Now, we've learned descriptive statistics. That was kind of the start of our study of statistics. That's dealing with numerical and graphical methods to look at patterns, summarizing information, presenting information in a form that makes sense or graph that makes sense. The other type of statistics is inferential, and that's what we're going to be more heavy in now. Inferential statistics use sample data to make estimates, decisions, predictions about a larger set of population data. We are trying to generalize to a population. Now, there are 5 components of inferential statistics. The population of interest, basically what it is, okay? What is our population? One or more variables to be investigated. Okay, what are we actually looking at here? And then the sample of the population units. So we want to take a sample with good methodology, which is why we've already learned, with good methodology. Which is why we've already learned good methodology for sampling. Fourth one, the inference about the population based on the information in the sample. And then a measure of reliability. How do we know if the procedure is actually working? What are we measuring? How are we measuring this? A newer term, something that we've actually learned before, we've been introduced to, is a point estimator or a point estimate. So a point estimator is a statistic that provides an estimate of a population. So basically, it's another term for a specific statistic that we're looking at. Just another way to say it. So the value is your point estimate. That is nothing new. But just a reminder, p hat. That generalizes to p. X bar hopefully generalizes to mu. S generalizes to sigma. All right? So these are unbiased estimators. The actual point estimate, so let's just say p hat equaled 0.04. That's the actual point estimate. It's the actual number. Okay? So I'm going to give a couple examples, and I want you to identify what it is that we're looking at. What is the population parameter, and then what is the statistic that goes along with it. Okay? So identify the parameter, the point estimator you're going to use, and then the value that goes along with it. So quality control inspectors want to estimate the mean lifetime of AA batteries produced each hour at a factory. They select a random sample of 50 batteries during each hour of production and then drain them under conditions that mimic normal use. Now, I'm not going to make you go through all these values and actually find them, but what we're looking at here is, this is a mean problem. This is an average. So we are looking at the mean here. So It's the mean lifetime of these batteries, and that's where it says right here. So we're going to be looking at mu, which would be the true, and this word is going to be important. I want you to use this anytime we're talking about the parameter. It's the true mean lifetime of AA batteries. So give the context. Whereas our sample statistic, the sample mean is X bar, and we would have to have that actual statistic. So I have it here. Here's some summary statistics. Mean is 16.718 hours. All right, so that's what we're looking for here. Second example, same question. Find those things. What proportion of U.S. adults would classify themselves as vegan or vegetarian? A Pew Research Center report surveyed 1473 randomly selected U.S. adults. Of these, 124 said they were vegan or vegetarian. So it starts off by saying what proportion. We should know this is a proportion problem. We're looking at P, and we're looking at P hat. So P is the true proportion. We want to say true proportion of U.S. adults being vegan or vegetarian. And the proportion we actually have to find, it says 124 out of them, so we take 124 out of 1473, and we get that as 418. That's our statistic. We got one more here. It says the quality control inspectors in Part A want to investigate the variability. You see variability. Usually we're going to think standard deviation by estimating the population standard deviation sigma. So sigma is the true standard deviation of battery life. And then S is what we're going to be generalized. We're going to use as from our sample, and that is, well, and actually we have to go back to this. It said the standard deviation from our was 0.664. That's our sample statistic. So, a little review of something we've done. But now we're going to take this information and we want to build these things called confidence intervals. It's a big part of inferencing. So when the estimate of a parameter is reported as an interval of values, which is very common, it is called an interval estimate, or more commonly, a confidence interval. So a confidence interval gives an interval of plausible values for a parameter based on sample data. And I want to make note that plausible is not the same as possible. Plausible means that we shouldn't be surprised if any one of the values is in the interval is equal to the value of the parameter. It doesn't mean all the possible values. It just means plausible. So yeah, so keep that in mind. It's not just possible, because anything is possible, but we want plausible, reasonable, plausible. All right? Confidence intervals are constructed so that we know how much confidence we should have in that interval. That's the part that some people get a little mixed up with, like what that actually means. 95% is the most common confidence interval, saying that we have a 95% confidence interval. That confidence level gives the overall success rate of the method used to calculate the confidence interval. That is that in this case, 95% of all the possible samples, the interval should capture the true parameter. So it's also considered a capture rate. Meaning you've got the parameter, which whatever that is, and given this net and saying that true parameter should fit um, into our net 95% of the samples. Okay. Now, to create an interval of plausible values, which is our confidence interval, we need to know two components. We need the point estimate, which is the middle, essentially, but it's whatever statistic we're using here. It's the midpoint of the interval and is surrounded by whatever margin of error we have. Okay, so the point estimate, again, is our statistic. We talked about those before. Plus or minus. So whatever range it falls into, let's say we have this confidence interval. The point estimate is right there, and we have the same size margin of error on either side. So if the margin of error is 2, then it's going to be 2 on each side of that point estimate. And that's what makes that interval or that range. So an example, it says a recent survey found that 65% of U.S. adults, again, we're looking at a proportion here, would be willing to admit to having extreme credit card debt with a margin of error of 3%. So the idea here is this is considered our E. Capital E is our margin of error. Okay. This is our P hat. It's from a survey, so it's a statistic. And we can build our confidence interval based off of that. We would say 0.65 plus or minus 0.03, meaning our confidence, our interval would be from 0.62, that looked bad, 0.62 to 0.68. That is our interval. Now, as a visual, you could see it like on a number line. We can take our number line, we can go 0.6, 0.65, 0.7, and our point estimate was at 0.65. That's right here. And we want to say our interval goes from 0.62 to 0.68. That's our confidence interval. That's our net that we're trying to catch the true parameter. We have whatever confidence level in it that it will catch it. All right. So using that term margin of error, the margin of error of an estimate describes how far at most we would expect the estimate to vary from the true population value. That is, in a whatever percent confidence interval, the distance between the point estimate and the true parameter value will be less than the margin of error. It should fit in that margin of error somewhere. Okay? With whatever confidence. So just to show a quick visual, if I take a 95% confidence level, and so let's just say sample size 20, you can see this is a similar visual to what we talked about with sampling distributions compared to the population. The gray is the population, the red is the sampling distribution. If I do one sample, the hope is that it's gonna this with this confidence level, the actual interval would capture that green line. And it does. Okay. We can do another one. It's capturing it. The green line is in there. I do 25 more. There are 2 of those 27 now that did not fit in there. Now, that's a 93% hit. Ultimately, it should be 95%. If we do 25 more, one of them didn't. So up to 94%. 25 more. Ooh, there's a few that didn't hit. So we're in the 90s still, but I keep doing it over and over again. What's going to happen? It should get closer and closer to that 95%. Should be capturing it. So we're kind of teetering between 95 and 94. Now that's the idea when we're taking a whole bunch of samples. But I do want you to just know how a good way to interpret this would be. And then we just got a couple things I want to finish up with. So it says, if we're interpreting a confidence level, if we were to select many random samples from the same population, about blank percent of the confidence interval is created would capture the true blank. And that would be parameter. So that's one way to do it. We've talked about another way, but really that's the idea, the true parameter in context. And this would be your confidence level. Again, we'll use 95 a lot. Again, more context here for the specific problem. So key pieces here. We want to state repeated sampling. That's expected. So somehow that needs to be in there. So if we state it like this, if many samples, that needs to be included. Some sort of capture. Some sort of way to capture the parameter, and then context. I do want to make note, it's frowned upon to use certain things like chance or probability. So those two things are frowned upon when using this, because we're saying with confidence it's going to capture this. We're not going to say there's a chance. So don't use those. Use the little detail that I gave you here. Now, I have a couple just examples. This says a survey of 500 doctors found 95% confidence interval for the proportion who exercise regularly to be between 27 and 33%. Now, think about that. That doesn't really matter in the context of the problem, but you can figure out that the point estimate was 30% and the margin of error was 3%. I just want you to be able to explain the meaning of a 90% confidence level. And I'm going to show it to you. So here's how I have it. It said if we were to select many random samples of 500 doctors, about 90% of confidence intervals created would capture the true proportion of doctors who regularly exercise. Okay, about 90%. That's what we're saying here with a 90% confidence interval. So, what z-score is bound the middle 95% of a normally distributed population? And what is the critical value in creating a 95% confidence interval for a proportion? And those two things are actually going to go hand in hand. This term critical value, it's also known as Z star. It's going to be a z-score. But it's going to be the positive or negative z-score that bound that percent. So if we're saying a 95%, we want to look at the visual of, okay, we have here and here on either side of our middle, and this is inside of here is 95% of it. Something we've done, back a while ago. But we want to be able to figure out what z is and what negative z is. So it's probably easiest just to figure out that makes up 2.5% on either side. So this ends up being 0.025, and this ends up being 0.025. And if you go to 0.025, you can use inverse norm in your calculator. You can use your table. But that should give us a z-score, and it actually gives us a z-score of negative 1.96 and positive 1.96. And that means our z-star, we're just always listing the positive version, is 1.96. That is considered the critical value that bounds 95% within the inside. That's a common one that we're going to use for 95%. The z-star, or the critical value, is 1.96. So follow up, what z-score bounds the middle 90% of a normally distributed population? What is the critical value? So same idea, just a slightly different visual. We have, again, we want 90% on the inside. So we want to find the z and the negative z for those. And again, inverse norm, it'll give us a z-star of 1.645, another common one that we're going to be using. but that's if you do inverse norm of 0.05 because there's 0.05 on either side. All right. We might be going opposite. We might be given the critical value of 2.41 and saying what is the level of confidence. So that what that means is kind of the opposite. We have a visual where we're looking at 2.41 and negative 2.41. We need to figure out what percent is in here. Okay? If you go to your table, you can find the values of that are less than the 2.41, that are less than the negative 2.41. We would have 0.9920, and then from this one, we would have 0.0080, and if we subtract them, that gives us what's in the middle, which has got to be 0.984. So if this is 0.984, this is 98.4% in there. This is a 98.4% confidence interval or confidence level. Okay? So that's how you can go backwards if you know the critical value. Typically, the confidence levels are going to be whole percents, and that's just normal. But for the sake of the question, we can do the same thing. So why don't you try this one? Find what the percentage in the middle would be. That would be your confidence level. All right, I have my work there. We were trying to find that middle percentage. So I found the z-score, sorry, the proportion of everything less than 2.155 and everything less than negative 2.155. Subtract them. I got 0.9684. That's a 96.84% confidence level. So just to wrap it up, we have a recipe. I'm just going to have you pause and write this down. This is essentially a recipe for all confidence intervals. We're also going to get into hypothesis testing. And they're all going to use the same things. We'll get into these more tomorrow and in the coming days. But these are all expected when it comes to the AP test. So we're going to get a lot of practice using all of these. And that's what I'm going to leave you at with for this section. This is just an intro to confidence intervals. We're spending a lot of time in the coming days on confidence intervals. This is chapter 8. We'll see you next time.